Hi all, welcome back to discussion on quantum optics. So in the last class we discussed Jaynes Cummings model, and today we are going to introduce the dynamics of Jaynes Cummings model. So the Jaynes Cummings model is basically describes a two-level atom and a single mode electromagnetic field. So its interaction can be represented using the Hamiltonian h cross omega 0 by 2 sigma z plus h cross omega a dagger a plus h cross lambda sigma plus a and sigma minus a dagger. So recall this sigma z is called inversion operator, which is sigma z is basically E minus GG. Okay, so remember this E and G are the two atomic level, and which is having the transition frequency of omega 0. So h cross omega 0 is the energy difference between the ground state and exit state. And a dagger a are the creation and annihilation operator for photons. Okay, so you can denote this hat a dagger and a cap, and sigma plus a and sigma minus a basically represents the interaction. Okay, so in order to study the dynamics of the system, it would be convenient to use the induction picture rather than the Schrodinger picture. So therefore, the Hamiltonian I can split into two parts. One is the free part, which is denoted by symbol H0, where H0 is h cross omega 0 by 2 sigma z plus h cross omega a dagger a, and the remaining part can be denoted by symbol H prime, where H prime is the interaction Hamiltonian, which is h cross lambda sigma plus a plus sigma minus a dagger. Okay, so H0 is called the free part of the Hamiltonian and H prime is called the interaction part. And using the interaction picture, the equation of motion can be denoted as H cross dou psi a by dou t equal to H prime I psi I. Now we have to find what is the H prime I. So the interaction part of the Hamiltonian interaction picture. So H prime I can found using e raised to I H0 t by H cross, H prime e raised to minus I H0 t by H cross. And we can calculate this H prime I using Baker-Campbell-Hausdorff formula. So suppose if you have two operators A and B, so e raised to A times B into e raised to minus A is basically B plus commutator AB plus half commutator A comma commutator AB plus etc. So therefore here H prime I would be equal to H prime plus H0 H prime commutator H0 H prime plus half into the commutator H0 and a commutator H0 H prime plus etc. Now in order to calculate this H prime I, it is required to calculate what is the commutator H0 H prime. Okay, so we already know the expression for H0 and H prime, so we can calculate this H0 commutator H0 H prime here. So H0 is H cross omega 0 by 2 sigma z plus H cross omega a dagger a, and H prime is this. Okay, now we can find the commutator. So there will be 4 commutation will come here, and that can be split using the normal commutation rule. So this part you can do it yourself and use these result, the commutator between sigma z and sigma plus or minus is plus or minus 2 sigma plus or minus, and commutator between a and a dagger is 1, and as well as the commutator between a and a, and as well as a dagger and a dagger are 0. So using all these result, it is possible to calculate H0 H prime. So I am not going to dictate all these steps here. You can see all the steps. Okay, so just pause the video and do it yourself, all the steps involved in this commutator. And you can show that when detuning delta equal to 0, where is omega 0 minus omega equal to 0. Remember, omega 0 is the transition frequency of atom, and omega is the frequency of the radiation. So when in resonance, so this delta equal to omega 0 minus omega equal to 0 means it's a resonance condition. So in resonance, this H prime I will be same as H prime, because in resonance this commutator H0 H prime would be 0. Okay, because we have got h0 h prime equal to h bar square lambda sigma plus a omega 0 minus omega minus sigma minus I dagger omega 0 minus omega. So if in reference this omega 0 minus omega would be 0, so both term would be 0, then therefore h0 h dash would be 0, commuted h0 h dash would be 0, and the interaction picture, the interaction Hamiltonian would be same as in the interaction Hamiltonian in Schrodinger picture. So therefore h prime I can write h cross lambda sigma plus a sigma minus a. Okay. Now consider the initial state. So here there are two subsystems here. One is the atom, another one is a field. Suppose initially the atom is in the excited state, and the number of photon in the field is n. So therefore the initial state I can write as the tensor product between the excited state E and the number state n. So number state n is a Fock state. Okay. So let us consider the atom initially in the excited state with the field initially in the Fock state, and I can use this notation. So this I can also write written as a ket E comma n. Okay, now this atom may de-excite. So even atom de-excite, this E become G, and the number of photon may increase to n plus 1 in resonance. So the another possible state is G, tensor product G and n plus 1. So the final state I can write as G, the tensor product between G and n plus 1, or it is also denoted as G comma n plus 1. So since the both state having the same energy, if omega 0 equal to omega, so this is a condition of resonance. Okay. Now a general state. So since these are the two possible state for the atom field interaction, so therefore the general state can be written as Ci of Ti plus Cf of Tf. Okay. So remember we have taken the field in the Fock state. Now Fock state is only one possibility. There are other possibilities as well. We already discussed earlier. There's a state called coherent state for the field. Okay, so that kind of state we will discuss later. Okay, so right now we are assuming the field is in the Fock state. Okay, and the atom can have two possible state. One is either excited state E or the ground state G. Okay. Now a general state would be the superposition of these two states. So we have two possible states. One is En and other one is Gn plus 1. So a general state would be the superposition of these two states. So En I denote by symbol I and Gn plus 1 denoted by symbol F. Okay. So a general state is Ci of T ket I plus Cf of T ket F. Okay. Now initially if the system in ket I state, then the Ci at time 0 must be 1 and Cf at time 0 must be 0. So these would be the initial conditions. Okay. So now using the interaction picture, our equation of motion would be H cross dou psi by dou t equal to H prime I, and this state I have already written as Ci of t E comma n, Cf of t G comma n. So remember this both Ci and Cf are the functions of time. Okay, and right side the H prime I would be H cross lambda sigma plus a sigma minus a dagger, and Ci E and Cf G n plus 1. Now if you look at the left side, so left side we have to do the time derivative. So Ci becomes Ci dot and Cf becomes Cf dot. Okay, so this dot, if you keep a dot above the symbol, that means there is a time derivative. And right side you have to act sigma plus a on En. So if you act sigma plus on E, it would be 0. Okay, so recall this fact. Sigma plus is the excitation operator, so sigma plus on the excited state is 0, and sigma minus on the ground state, sigma minus is the de-excitation operator, sigma minus on the ground state is 0, and sigma plus on ground state will become excited state, and sigma minus on excited will become the ground state. So you have to record all these action of operators. So just act sigma plus a on En, that would be 0, whereas sigma plus a acting on Gn plus 1 would give En. Okay, so sigma plus a action on this particular state will give a non-zero state, and that is what is written here. It becomes Cf of t root n plus 1 En, and sigma minus a dagger acting on this state would be non-zero. The atom would become ground state, and a dagger, that is the number of photons will be created, one photon would be created, and that expression would become Ci of t root n plus 1 g n plus 1. Okay, now next we can just compare the coefficients from both of two different state, because here the state En and Gn plus 1 are orthogonal. So therefore these coefficients of each state must be equated separately, must be equal separately. So if you just compare the coefficient of state En, so if you compare the coefficient of state En, it will be on the left side it is IH cross Ci dot, and right side is it is H cross lambda root n plus 1 Cf. Okay, so that would be one equation. And if you look at the coefficients of state Gn plus 1, the left side it is IH cross Cf dot. Okay, so better keep a bracket here. Okay, IH cross is common to both, so IH cross Cf dot time equal to H cross lambda root n plus 1 Ci of t. Now it is possible to solve this kind of differential equation. So we have two first order equations, and they are coupled. Ci dot is connected with Cf, and Cf dot is connected with Ci. So what we have to do is okay, so let us suppose this is some equation. Okay, so there are many equations we have already written. I have to keep some numbering. Okay, so let us start with, this is equation number 1, and this can be equation number 2, and H prime. So this can be equation number 3, and equation number 4, equation number 5, and so this can be equation number 6 and 7. Okay, so just take the time derivative of equation number 6. So if you take the time derivative of equation number 6, the left side will become IH cross Ci double dot, and right side would be H cross lambda root n plus 1 Cf dot. Okay, but Cf dot can be substituted from equation number 7. Okay, so remember IH cross Cf dot is H cross lambda root n plus 1 Ci. So if you substitute this Cf dot using 7, then this become lambda root n plus 1, Cf dot would be 1 by I lambda root n plus 1 Ci of t. Okay, so just rearrange this equation, you will get a second order differential equation time. So Ci double dot plus lambda square of n plus 1 Ci equal to 0. So once you solve this, it would be an harmonic function. Okay, so harmonic function of time. So Ci of t would be a cos lambda root n plus 1 t plus b sine of lambda root n plus 1 t. Now it is possible to find these coefficients a and b by using the initial conditions. So we know that at time t equal to 0, Ci of 0 is 1. So that is the initial condition we already set. And from that we can show that this b becomes 0 and a must be 1. So therefore Ci of t become cos of lambda root n plus 1 t. And in the same way we can find the relation expression for Cf of t. So that I am leaving to you, so you do it yourself as homework. Okay, so this Cf of t will become minus I sine of lambda root n plus 1 into t. Okay, so we have got the expression for Ci and Cf. So therefore the state vector I can write psi of t is cos of lambda root n plus 1 t times En minus I sine of lambda root n plus 1 t into g n plus 1. So next from this coefficient we can calculate what is the probability to find the system in the state I, in the initial state En, and the final state and the state Gn plus 1. So the probability to find the system in the ket I, which is denoted by symbol En. So this can be find by calculating the mod square of the coefficient of that corresponding state. So the coefficient of the state get En is cos of lambda root n plus 1 t. So the probability to find the system in that particular state is denoted by symbol pi of t, which is mod ci square, and that will become cos square of lambda root n plus 1 t. Similarly, the probability to find the system in the state f, okay, the state f is nothing but the state g n plus 1. Okay, so that is denoted by symbol pf, and it is equal to sine square of lambda root n plus 1 to t. Okay, now we can note that the system would be either in the state I or in the state f. Therefore, the sum of these two probability must be 1, and you can verify it. The pi of t plus pf of t is equal to 1. Okay, so let us keep some equation number for this. Okay, this can be equation number 8, 9, 10, and this probability can be equation number 11, and this can be equation number 12. Okay, so next our aim is to calculate the expectation value, so that gives the dynamics of the system, how the system evolves with time. We can the better quantity is the inversion operator, so we can calculate the expectation value of inversion operator. So recall sigma z is the inversion operator, which is nothing but EE minus GG. Okay, so the inversion operator, the expectation value written by symbol W of t. So it is the expectation value between between the state psi of t for the operator inversion sigma z. Okay, so I can expand psi of t by using equation number 10. Okay, so using equation number 10 I can expand it. Okay, for the time being I have denoted the coefficients as Ci and Cf, but I already know what is the expression for Ci and Cf. Okay, so just substitute the expression for psi of t, get psi of t and bra psi of t, and sigma z is nothing but EE minus GG. So do all these calculations. So I am leaving to you to do all the calculations. So the many of the terms in this would become 0. So finally what you will get is it would be equal to mod Ci square minus mod Cf square. So all these steps you can do it yourself. Okay, it is not very difficult, so I will just explain the first term. Okay, so if you look at the first term, so this is the bra psi. So bra psi has two terms, bra En Ci star. Okay, so just take the product between this term with EE and this. Okay, so that would be the bra En, then Ci star, get E, bra E, then Ci of t En. So that is a one term we have. Okay, now the Ci star is just a number. I can take the Ci star outside, and Ci of t is just a complex number that can also be taken outside the inner product. Okay, I have missed n here. Okay, now this inner product would be simply equal to Ci star of t. This inner product will be simply equal to Ci of t, because Ci star of t, the remaining thing is En. This inner product is 1, and also here the inner product is En and En. This inner product is also 1. So therefore the finally you will have and the product between Ci star and Ci, that would be mod Ci square. So that is basically this first term. Okay, so I have just shown to you how to calculate one of this term. So similarly do all this calculation, we will get many number of terms here. So do all the calculations. So many of them would become 0. Only two non-zero quantities would come. So one non-zero quantity I have already shown to you, that would be mod Ci square. The next non-zero quantity would be minus mod Cf square. So that you can do it yourself. And mod Ci square is nothing but the probability to find the system in the state I, and mod Cf square is the probability to find the system in the state F. Okay, so therefore this W of t, the expectation value of inversion operator, or is called simply called inversion, is the probability to find the system in the state I minus the probability to find the system in the state F. So that is basically the difference of the probability in these two states. Okay, so now from this W of t we can easily find out whether the system is in this is state I or in the state F. So if the system is exactly in the state I, the W of t would be 1. If the system is exactly in the state F, the W of t would be equal to minus 1. So if the value of W of t is in between 1 and minus 1, so that means the system must be in a superposed state. Okay, so that is the relevance of this W of t. So from W of t, we can easily point out what would be the possible state of the system, whether it is in the state I or in the state F or in the superposed state. Okay, so if the system is state I, then Pi of t would be 1 and Pf of t is 0, so W of t would be 1. And if the system is exactly in the state F, the Pf of t is 1 and Pi of t is 0, W of t equal to minus 1. Okay, so therefore the W of t value basically varies between the plus 1 and minus 1. Now we can calculate this W of t also. Okay, so W of t is always between plus 1 and minus 1. W of t plus 1 means the system in state I. W of t minus 1 means the system in state F. Okay, so it is always between plus 1 and minus 1. So you can calculate W of t because we already know the expression for Pi and Pf. This Pi is nothing but cos square of lambda root n plus 1 into t, and Pf is sine square of lambda root n plus 1 into t. So we can calculate this W of t exactly for this particular system with the Fock state. So W of t is cos square lambda root n plus 1 t minus sine square lambda root n plus 1 t. And you just do the simplification. I can expand cos square and sine square in terms of cos. So finally you will get the result as cos of 2 lambda root n plus 1 into t. So that means W of t dynamically varies with time. It changes with time and it changes harmonically with the frequency 2 lambda root n plus 1. And this 2 lambda root n plus 1, this frequency is called Rabi frequency, and hereafter we are going to denote it by the symbol capital omega. So capital omega of n equal to 2 lambda root n plus 1. So just let's keep some numbering here. So we have keep this Pf 12. So this can be equation number 13, and this can be equation number 14, and this can be equation number 15. So finally the inversion W of t is cos of omega of nt, for capital omega is the Rabi frequency. And we can plot this W of t for the different photon number. Okay, for some photon number, for any photon number it will be harmonically varying. So this frequency or this time period basically depend upon, it's a function of n, so it will depending upon n. So when n increases, the number of photon increases, the frequency increases. So this gap is basically connected with the time period. Okay, so the increasing frequency means the decrease of time period. Okay, so if you look at this the dynamics of the system, when the system is initially in the excited state with the total number of photon equal to n, the inversion operator varies in this way. So the inversion operator, the expectation value of inversion is oscillating between the plus 1 and minus 1 harmonically. So what it means, so if W of t plus 1 means initially exactly in the system is exactly in the excited state with n photon, and a W of t minus 1 means the system atom is in the ground state with the number of photons n plus 1. Okay, so here in this state W of t is plus 1, in this state the W of t is minus 1. Okay, but I can see here the W of t is harmonically vary between the plus 1 and minus 1. So for most of the time it is in between plus 1 and minus 1. So that means the system would be in the superposition of these two states for most of the time. Okay, so it is in the superposed state of I and F. Okay, and moreover, you can see that the atom spontaneously de-excite and become the ground state, and from there it will become spontaneously excite, and it become in the state E. So you can see a spontaneous de-excitation as well as a spontaneous excitation in this system. Okay, so this expectation value of inversion operator periodically changes with time, and this is called Rabi oscillation, more correctly quantum Rabi oscillation, because this is a quantum mechanical system. And physically it means the excitation de-excitation of atom. So W of T 1 means the atom is in excited state, and W of T minus 1 means the atom in the ground state. So plus 1, W of T is always between the plus 1 and minus 1. Okay, so if it is exactly between plus 1 and minus 1, that means the system is in the superposed state. And this oscillation shows that the atom can spontaneously emit a photon and it can de-excite. Similarly, the atom can absorb a photon and it can excite. So you can see a spontaneous de-excitation as well as a spontaneous excitation in the this kind of system. Okay, now the surprising fact is such oscillation is possible even in the absence of photon. So that means if, even though if n equal to 0, if n equal to 0, the omega of n is not 0, omega of n is 2 lambda. So that means the W of t would be cos of 2 lambda t. So you can get the excitation and de-excitation of photons even if the initial number of photon is 0. So this kind of, we can see this kind of oscillation for inversion operator even in the absence of photon. That is, initially there is no photon present and the atom in the excited state, and the atom de-excite to the ground state, and further it excite, de-excite, excite, even initial photon is 0. So this kind of oscillation is called vacuum Rabi oscillation. Okay. So this gets the idea about the spontaneous emission, because we know that a kind of emission called stimulated emission. So stimulated emission, some photon presence is required, but the atom can de-excite even in the absence of photon. So that kind of emission is called spontaneous emission. So the Rabi oscillation, the vacuum Rabi oscillation, gives some idea about the possibility of the spontaneous emission. Okay, so what we have discussed so far is, so if you consider a system, an atom with two state, a ground state and excited state, and the field is in the Fock state. So initially the system has n number of photon, then the two possible states are En and Gn plus 1. And if the Hamiltonian, the Jaynes Cummings model is Jaynes Cummings model is working here, then the system can move from the state En to Gn plus 1 and vice versa with some frequency, and that variation is called the Rabi oscillation, and the Rabi oscillation frequency is given by 2 lambda root n plus 1. So by increasing the number of photon, the Rabi oscillation becomes possible. And what it means by Rabi oscillation, it is the transition between the excited and the ground state. So there can be spontaneous emission, spontaneous de-excitation of atom from the excited state, and as well as a spontaneous absorption or spontaneous excitation of atom from the ground state. So this will keep on happening, and at any time, if you could able to stop this transition, then we can get the system is in the a superposed state. Okay, so if it is W of t is exactly plus 1, then the atom in the excited state, and W of t is exactly in minus 1, the atom in the ground state. If it is in between, it will be in the superposed state. Okay, now next we move to the possibility of coherent state, the dynamics of Jaynes Cummings model in the presence of coherent state. That is, suppose if the photon state or the field is in the coherent state, what would happen? Okay, so if the initial state of the field is in the coherent state, the coherent state usually denoted by symbol ket alpha, and basically it can be expanded in the number state. So ket alpha can be written as sum over n Cn, which is e raised to minus mod alpha square by 2 sum over n alpha raised to n by root n factorial ket n. Okay, so then so the initial state is ket alpha, so therefore the psi of t I can write Ci of t ket I plus Cf of t ket f, where this ket I Ci of t sum over n Cn Ne plus Cf of t sum over n Cn n plus 1 times g. Now the expression for Cn we already know. The Cn is e raised to minus mod alpha square by 2 alpha raised to n by root n factorial. This is what is by Cn. Now we already got the expression for Ci and Cf. Okay, I can use it here. So Ci I can write as cos of omega of nt by 2, and Cf is minus I sine of omega of nt by 2, where omega of n is called Rabi frequency, which is 2 lambda root n plus 1. Now I can calculate the atomic inversion in this particular possibility. Okay, so here the system initial state I, the state I is E alpha, and this also will be coherent, both would be the coherent state. Okay, so W of t is Pi minus Pf. So Pi is sum over n mod Cn square cos square of omega n, and Pf is sum over n mod Cn square sine square of omega n. So sum over mod Cn square is common, so this becomes sum over n mod Cn square cos of omega of nt, and Cn we already discussed, which is e raised to minus mod alpha square by 2 alpha raised to n by root n factorial. So therefore W of t would be an infinite sum. So it is sum over n e raised to minus mod alpha square by 2 alpha raised to 2n by n factorial cos of omega n of omega of nt. Okay, now it is good to note that mod alpha square is nothing but the expectation value of the number of photons in the state, it denoted by symbol this bracket n. So this become e raised to the expectation value of e raised to minus expectation value of n sum over n, the expectation value of n all raised to n by n factorial cos of 2 lambda root n plus 1 into t. So recall this the coherent state, the photon distribution is of having the Poisson distribution, and using that expression I can write this. Okay, now if you try to plot this W of t, it is not very easy to plot this W of t. So you may need the computers to draw this purpose. So there are many softwares which is available to draw these graphs. Either you can use GeoGebra or any graphing software, or you can use Python program to graph such things. Okay, the only thing is this is not a single term. Here we have then it is a sequence. So here basically it runs from n equal to 1 to infinity. So initially this summation is infinite summation, but you can truncate the summation for your purpose, because if you look at this denominator is square root of n factorial. So the value of these terms would decrease on increasing the number of value of n. So you have to limit how many terms you have to take in practically. So for practical computation you will limit n for some values. So that would also depending upon the average number of photons. So if the average number of photon is 10, and then you may not be need to take 100 terms. No need to sum n from 1 to 100. You can truncate it maybe 50 or 60. So depending upon the situation you have to do it. But if the average number of photon is 100, so obviously you may have to take more number of terms. Okay, so to how many number of terms you will take it here, what is the limit, the upper limit of this sequence, that would obviously depending upon the average number of photon. But basically it is theoretically it is up to infinity, but practically you cannot sum up to infinity, because that summation will never end, because you can keep on summing, it will never end. So for practical purpose you have to keeps some upper limit for the summation. So you can do this plot using some graphing softwares or Python programming. So that part I will show it later, how to do this graph plotting using some software that I will show it to you. Okay, now if you draw this plot for average number of photon is equal to 5, then the graph would be approximately will look like this. Okay, so it is not an exact graph, almost it will look like this. Okay, so what it shows, so initially the system, the atom is in the excited state because the W of t is +1, but after that it is not coming to -1, it is not the atom is not coming to the ground state. After that it is in the superposed state, and you can see that after some time, okay, maybe this time I did not by symbol t1, and this time I didn't by symbol t2. So between the time t1 and t2, the W of t is 0. This W of t is completely 0 between t1 and t2. So what it means, the W of t is 0 means the system is in the exact superposition of excited and the ground state. So that means when W of t becomes 0, okay, recall W of t is Pi of t minus Pf of t. That means the system is having equal probability to find the state in the system in the state I and as well as in the state F. We have equal probability. So that means the system must be in some state like this, 1 by root 2 get I plus 1 by root 2 get F. We have the equal probable state. Okay, so system exactly it is having an exact superposition of the exact superposition means it is having the equal probability for the state I and state F. So this kind of situation is called collapse. So in the system is in collapse for the time duration between the T1 and T2. And after T2, so between T1 and T2, there is no dynamics for the system. The system remains in the exact superposition of the ket I and ket F, and after that it is changing. Okay, so remember, if W of t is greater than 0, what it means? W of t greater than 0 means Pi must be greater than Pf, and W of t less than 0 means Pi is less than Pf. Okay, and W of t equal to 0 means Pi equal to Pf. Okay, so W of t is 0, so this line, this horizontal line is W of t equal to 0, so that we have an exact superposition of this ket I and ket F. The system is in the exact superposition. But if W of t is positive, then that means the system is having the greater probability to find the state I compared to the state F. And if W of t is minus, so if the value of W of t is below that horizontal line, so that means the system is mostly in the state F compared to the state I. Okay, and that is not exact superposition. So if the system is in the exact superposition, that is called collapse. And after collapse, usually the system may change its superpositions, the type of superpositions. Then so that change is called revival. So from collapse, if W of t, the inversion, become non-zero, then it becomes revival. So you can see a sequence of the collapse and revival if the photon is in the coherent state. And this kind of state is having very importance for particularly applications of quantum technologies, particularly if you look at the quantum computation or quantum information processing. These kinds of states, that is the exact superpositions of the state I and state F, it is very important. These states are also called the entangled states. Okay, so when W of t becomes 0, the state is said to be in collapse. So during the collapse, the atom is in the maximal entangled state. So these are the called the maximal entangled state, and it is very important for technology like quantum computation, quantum communication, etc. Okay, so I can summarize what you have discussed so far. So if you take a two level atom with two possible state E and G, and if the system, the photon is in the Fock state, then the atom may de-excite to the ground state, and as well as it can excited from the ground state to excited state harmonically with time. And if you look at the W of t, it varies between +1 and -1. Okay, and you can see that it continuously very harmonically varies between +1 and -1. And if you look at this exponent is cos of omega n of t, where omega of n is 2 lambda times root of n plus 1. But okay, so if w of t is exactly +1, then system is in the state get I, and if w of t is exactly -1, the system is exactly in the state F. But if it is between +1 and -1, it will be in the superposed state. Psi of t, it is Ci of t get I plus C of t get F. It is a superposed state. Okay. Now, if you look at the system, but the initial state is a coherent state. So if the initial state is coherent state, then the dynamics is not that much simple. You can see the dynamics is like this kind of things. You can see a collapse phenomena here, revival, and plus again you can get some collapse, and you can get some revival, etc. So if you could able to increase this collapse time, then the system is in the maximal entangled maximum entangled state for a very long time, and you can use this kind of states for quantum communication purposes, and as well as the quantum computation purposes, and so on. Okay, so this is one of the application of quantum optics. If you look at the technologies of the present technologies of this era, and it is very much useful. So you can it is possible to manipulate your atomic system with your the field states. Okay, so if you have the coherent state and Fock state, you can control. So sometimes it is possible to make more interesting states for our need. Okay, so that's all about the dynamics of Jaynes Cummings model. So we can stop it here. So in the next class, we'll discuss another discussion about the dress state in quantum optics. Thank you.